Okay, another way to explain the concept of imaginary numbers is to think about a piano and how each key produces a different tone. And the volume is going to change that amplitude, so the volume of all the keys, how loud it's going to be. That's how the real number is going to affect the signal. But now imagine that there's a filter and it makes some keys sound louder and some sound softer, and that, depending on the frequencies. So the complex numbers, it just allows an extra dimension of calculation. And really the whole concept of imaginary numbers, the application of them, is beyond my expertise. So I'm just dealing more with the mathematics behind it. So if you want to know more about this, you'll have to just Google it. So let's go ahead and continue. All right, we've already talked about x squared and how if you tried to solve this problem, you would try to take the square root of both sides. Well, when you do that, the square root of a square is just going to be x. But when you get to the square root of -1, how can you find a number that when you multiply it by itself, it's going to be that same number? Because you've got -1 times -1, and that's +1. +1 times +1 is still +1. So there's no way that you can answer this. So they decided that they would just call it I. So I is equal to the square root of -1. So anywhere you see an I, you can replace it with the square root of -1. All right, here's some simplifying problems. In order to simplify, you're going to have to remove the imaginary part first. So in other words, you rewrite this as the square root of -1 times the square root of 36. We just said the square root of a -1 is I, and we know the square root of 36 is 6. So the square root of -36 is simply 6i. For problem 2, the square root of -28, again, you're going to rewrite it. We know the square root of -1 is I. And the square root of 28, that's not a perfect square, but we talked about how you break this down. That's going to be 4 times 7, and then that'll be 2 times 2. So you have a pair of 2's, and you have the 7 remaining. So that's going to be 2 square root of 7. And don't forget, you still have to multiply it times I. So you end up with 2i square root of 7. So based on that, go ahead and press pause, Ms. Henley, and let the students see if they can do number 3 on their own. All right, guys, hopefully you did this one right. You have the square root of -1 times the square root of 50. The square root of -1 is I. The square root of 50 is not a perfect square. So you have a pair of 5's, so you get 5 square root of 2, but you still have to multiply it times I, so you get 5i square root of 2. Now there is, on your calculator, there is a mode button that you can press to make sure your calculator will express imaginary numbers. So if you'll hit the mode button on your calculator, and scroll down to where you see A plus BI. That should be highlighted. If it's not highlighted, you need to use your arrows and go over and highlight it and hit enter. That way, when you type in a question like, say you typed in the square root of -36, your calculator should give you a 6i. If your calculator gives you some type of error button, excuse me for a moment. If your calculator doesn't give you a 6i, then this is what you have to do to change it. And hopefully everyone has got that figured out. All right, there are patterns of I. If you continued this pattern, like I to the first, I squared, I cubed, I to the fourth, if you continued this, it would just repeat. So I to the 5th is just going to be I to the 6th, is going to be negative 1. I to the 7th is going to be negative I. And I to the 4th is going to be 1. And it just keeps repeating this pattern over and over and over. And I remember this pattern by just thinking to myself, remember you were younger and you would tease someone if you'd won a game or something like that. You would say, I won, I won. But instead of thinking of it as WON, think of it as the number 1. So I won, negatives in the middle. So I won, negatives in the middle. That's how I remember that little pattern. So if you were asked to find, oh, sorry, that should be an 8. If you were asked to find something like I to the 10th, so if I said, okay, hey, what's I to the 10th? You could simply just count, that's 4, 5, 6, 7, 8, 9, 10. So that would be negative 1. That's kind of tedious to do that. So I just remember if the exponent that I'm raising my I to is divisible by 4, it's going to be a 1. And if there's a remainder, then it's just going to be whatever that remainder is. So for example, if I had I to the 15th, well, I know 4 will go into 15 3 times, but it has a remainder of 3. So I know my answer is negative I. So you say 4 goes into 15. Doesn't matter how many times it goes. What matters is the remainder. Whatever the remainder is, that's what your answer is going to be. And it'll work for, I to the 100th, I to whatever. This pattern always repeats. Now, your calculator will do this. The only problem your calculator has is if you try to enter exponents bigger than 8, sometimes it gives you a crazy answer. So the best way I've found to deal with this is, say you wanted to find something like I to the 30th. You can't really type that in and be guaranteed your calculator will give you a correct answer. You literally have to hit the I button 30 times, like I times I times I. And if you're not sure where the I button is, it's second, and then it's the decimal point. And that's how you get to the I on your calculator. So that's just something if you want to save yourself some time. But honestly, I think it takes longer just to type in an I 30 times than it does just to simply, follow this little pattern that we talked about. All right, you have a foldable, and this is where you can kind of start taking notes on that. I've got that printed out on colored paper. And all I'm going to be adding to this is a complex number is any number that can be written in standard form. So this is what standard form looks like, where this number is the real part and this number is the imaginary part. So you have a real part and an imaginary part. And this is just the standard form for it. You can actually plot these. So if you wanted to plot, and it's kind of interesting how this works, because you plot it just like you would an ordered pair. So if I told you to plot the complex number 2 minus 3i, you kind of think of it like 2, negative 3. So you go right 2 and down 3. Because the real axis is the x-axis. The imaginary axis is the y-axis. So to graph this number, you basically just graph 2, negative 3. So look at this one, negative 1 plus 2i. So negative 1 plus 2i. So I want you to think about what this one would look like. I'm just going to plot one and see if you can tell me what it is. So I'll give you a second. So look at that point and see if you can tell me what complex number that represents. So you can press pause. All right, hopefully you guys said it was negative 4 minus 3i. That would be the answer, negative 4 minus 3i. All right, adding complex numbers. Adding complex numbers is pretty much the same as adding any type of number system. You just add the like terms. So the real part adds to the real part. The imaginary part adds with the imaginary part. So 2 plus 4, that's 6. 3i minus 6i is negative 3i. So that will be your answer for the first one. Go ahead and see if you can try the second one. Okay, hopefully you guys got 11 positive 8i. So 11 plus 8i. Subtracting, it's the same thing. You just have to follow the subtraction. So go ahead and try these next two examples and pause it and then check back and see if you got it correct. All right, hopefully you got these two answers, 5 minus I and 3 plus 10i. All right, multiplying is a little more difficult because you have to remember this one little fact right here. I squared is equal to negative 1. So anytime you run into I squared, you just replace it with a negative 1. So when you're distributing 2i times 6 is 12i. 2i times 5i is 10i squared. Well, I squared, remember we just said that it's equivalent to negative 1. Well, the operation between the 10 and the I squared is multiplication. So it's really 12i plus 10 times negative 1, which would be 12i minus 10. Well, they want us to write it in standard form. So to write it in standard form, you need to switch it around and make it negative 10 plus 12i. So you try this one and see if you get it right. All right, for this one, you have to use the double distributive property. So you get 15, and then you get negative 20i plus 6i minus 8i squared. Well, now you've got like terms. Negative 20 plus 6 will give you negative 14i. And then remember, we're replacing I squared with negative 1. So that's going to end up giving you 15 minus 14i plus 8. And now you have like terms again. Add those together, and your final answer is 23 plus 14i. Okay, I added these two examples just because they do sometimes come up. When you multiply negative 3i times 2i, you just, like we did before, multiply the number parts, multiply the i's, and remember that I squared is really just a negative 1. So your answer for this is just 6. But when you do a problem like number 2, before you can multiply, you can't just say negative 12 times negative 2 is positive 24, because you have to remove the imaginary part first. So the shortcut is, if it's in a negative under the square root, you simply remove that negative, and that's going to be an I. So really it's I square root of 12 times I square root of 2, which gives you I squared square root of 24. Well, we know that I squared is negative 1, and 24 can be broken down using your table. And you have a pair of 2's, and you have a 6 left over. So 2 square root of 6 replaces the 24, because that's what you just did. You just broke it down, you simplified it. So the final there would be negative 2 square root of 6.